All right, we're going to start looking at getting energy from nuclear reactions for good and for evil, nuclear fission and nuclear fusion. Now, when we go back to this little chart here, we recall that the iron 56 nucleus is the most stable. And people realized, well, if we could get lighter nuclei to come together, to fuse together, to form heavier nuclei, those heavy nuclei are more stable than the lighter nuclei. Well, if the heavy nuclei are more stable, that means energy will be given off, and as we found out with the fluorine, it's a lot of energy given off. And they said, well, that's great, but we can't do that. Okay, well, let's look at the other way then. What if we have really heavy nuclei, such as uranium, and what if we could split this heavy nucleus up so it forms lighter nuclei? Well, those lighter nuclei will be more stable than the heavy nucleus. So then that should give off some energy too. And looked at it, yeah, but can we see that this giving off energy isn't going to give off nearly as much energy as this would? They said, yeah, but we can't do this, so let's do this. Let's find a way to split heavy nuclei into lighter nuclei. Since those nuclei will be more stable, energy would be given off. And note, iron 56 is the most stable. So as we go from heavy back towards iron 56, energy will be given off. And that process is nuclear fusion, or excuse me, nuclear fission. Heavy nuclei can divide into smaller nuclei and one or more electrons or beta particles. Okay. And note, since these are nuclear reactions, there should be a large amount of energy released in this reaction. And so what they found is that if you took uranium-235, turns out uranium-238 doesn't do this, doesn't fission very nicely. But uranium-235, if you get enough of it, if you get enough uranium-235, it just, it spontaneously is giving up neutrons. It decays, it gives up neutrons, and forms various things. And so many different things have come out that different books are going to have this equation balanced many different ways, because a whole bunch of different smaller, lighter nuclei came out of this. But what we see is a 235 gets hit by a neutron, and then that gives us strontium-90, xenon-143, two lighter nuclei. This one nucleus is split into two lighter nuclei, which means this side is more stable than this side, so energy is given off. All right. And much more importantly, energy is given off, that's important, but also three more nuclei get formed in this reaction. It turns out to start this, all you need is a critical mass. All you need is enough uranium-235 nuclei close together. And so if you bring enough uranium-235 nuclei close together, a neutron will be given off that will slam into a uranium-235 and do this reaction, which gives off three neutrons. Well, what are those three neutrons going to do? They're going to find three uranium-235s and do this reaction again. So now, but each one of those three reactions gives off three neutrons, so that gives us a total of 9 neutrons now flying around, which will react with 9 uranium-235s. Each one of those gives off 3 nuclei. Now we've got 27 nuclei, or neutrons flying around, which will react here, and we get what's called a chain reaction. Every time the reaction goes, it gives off more neutrons that make even more reactions. It gives off even more neutrons that make even more reactions. And this whole thing, this whole process, gives off a whole lot of energy over a very, very short period of time, only like milliseconds. And so whenever energy is given off very, very, very quickly, we call that a bomb. This gives us an uncontrolled chain reaction. This was our first atomic bomb, this uranium-235 bomb. Okay. And all it takes is, well, a lot of good engineering. All it takes is kind of a misnomer there. It takes a whole lot of work. But basically, you just have to find a way to get two masses of uranium-235 that are separated from each other, so neither one is the critical mass. They'll be totally safe. You have to slam them together fast enough that they form one big ball of uranium-235 that is above the critical mass, and as soon as that happens, boom, the bomb goes off within milliseconds. All right. Note, 8 times 10 to the third joules of energy. That's the equivalent of 20,000 tons of TNT will get released from every 1 kilogram of uranium-235. Ooh, well, that's not good. That's using energy for bad purposes. And we will not debate good versus evil of nuclear reactions in this class, but I think bombs tend to go towards the evil side. All right. Then someone got an idea. Okay, the problem with that reaction is that it's a chain reaction. Every time the reaction goes, 3 more neutrons get put into the mix, so now it goes 3 times more, and then 3 times more than that. What if we found a way to absorb these neutrons, get rid of these neutrons before they had a chance to run away with this chain reaction? So what if we put in something that for every 3 neutrons that were given off, say, well, we'll put it this way, for every 6 neutrons given off, it absorbed 5 of those neutrons. So then we can harness this power and we won't have a bomb. So we put our uranium, we get our uranium, and we control the reaction by absorbing the excess neutrons. And then we use the heat from the reaction, because it gives, even though it's not a chain reaction, the overall reaction is giving off a lot of heat. We turn water into steam, which turns a turbine, and that generates electricity, and we get a nuclear power plant. All right. So, yeah, so that's good. And so now we've used our idea of nuclear reactivity and changing heavy elements into lighter ones through this nuclear fission process into something good, nuclear power plant. Now, nuclear power plants in general are good because they don't pollute the atmosphere unless, of course, you go all Chernobyl and have a reaction, or 3 Mile Island. It's just, that's the problem with nuclear power. It's just, when it's working, it's very nice and it's very clean and doesn't pollute the environment. It's just that the products of the nuclear power plant are bad. They're very radioactive. And if something goes wrong, it goes really, really wrong. So, yeah, that's not good. All right. Then someone had an idea. Unfortunately, they had the idea while they were building the atomic bomb. They said, okay, but you know what? We've looked at this before. We've looked at the chart already. We're trying to take the heavy elements and make lighter ones. There we are. We're trying to go from here to here, and that'll give off energy. But man, if we could go from here to here, look how much more energy would be given off. But they said we can't do that. And someone asked, well, okay, you might ask, why couldn't we do that? The answer is we couldn't generate the heat to take lighter elements, lighter nuclei that are positively charged, slam them together such that they create a heavier element. When the nuclei are positive charge and they're repelling each other quite a bit, just takes a lot of energy in the form of heat, and we just can't reliably generate that heat. And then someone said, well, wait a minute. Didn't we generate a whole lot of heat in this atomic bomb when we took our uranium and did that? Didn't that generate a whole lot of heat? Yeah, this reaction here generated a whole lot of heat. And they did the calculation. Turns out this reaction generates enough heat to get our lighter elements to fuse into heavier elements. And so we've come up with nuclear fusion, combining the small nuclei into larger ones. Something to note, this is something that actually does take place in the sun. That's where we first saw it. And we fuse the lighter elements into heavier elements. The thing is, these reactions take very, very high temperatures to slam those nuclei together, so they're called thermonuclear reactions. Thermo for the amount of heat you need to get this to work. Now, a few things. Let's look. When you look at the sun, no, you don't have to memorize this page here. But when you look at the sun, these are the reactions that are happening in the core of the sun. And balanced in everything, it's two hydrogens meet with two hydrogens to form two deuteriums and beta particles. And then when you look at the baryon and the lepton numbers, you realize two neutrinos need to get made because you generated two positrons here. Two positrons means two neutrinos. And then you go through this. And an interesting thing happened, and it's actually fairly recently. There was a problem because when you look at this overall reaction, we find out that the net result is 4 hydrogen nuclei fused to form 1 helium nucleus, give off 2 anti-electrons, 2 positrons, 2 neutrinos, and 2 gamma rays. And when we look at what's coming from the sun, okay, we know there's lots of hydrogen in there. We can see there's helium in there too, the product, so that makes sense. We can see, okay, there's positrons coming from the sun, there's gamma rays, but we had trouble with the neutrinos. One of the big problems we had was we found the amount of neutrinos coming from the sun is only about 1/3 the amount of neutrinos you would expect if this was right. And actually detecting neutrinos is very hard, so that was the first thing as well. Are we even detecting the neutrinos correctly? Because they're very, very difficult to detect. They just don't interact with matter very much. And they said, yeah, the more we made the experiments better, the more refined we did it, we still had a problem that we're only getting about 1/3 the amount of neutrinos that this equation would expect. Until it was about 5 years ago or so, maybe 10 years ago, actually no, about 5 years ago, what they found was it turns out there are 3 different types of neutrinos. And our experiment only measured one type of neutrinos, and neutrinos can just turn into the other types of neutrinos on the fly. If you have one type of neutrino going through space, it'll spontaneously turn into the other type of neutrino. So it turns out we were only detecting 1/3 of the actual neutrinos given off by the sun because they were always interconverting into the other neutrinos. So once we realized there's 3 types of neutrinos, they're interconverting, now it totally makes sense. Of course we were only seeing 1/3 the amount of neutrinos because we're only detecting one kind. We didn't even know the other 2 kinds existed. Once we found they existed, boom, it worked right. And now we're pretty confident that this is what's happening in the sun. Note, you do not have to memorize these equations. However, on the exam, if I gave you these things, I'd expect you to be able to realize there's a positron here and be able to appropriately balance these equations. All right. So let's look at the advantages of fission if we want to generate energy. Okay, because what we can see when we look at all these reactions, a whole lot of energy is released, and our product is like helium. We've got helium nuclei and stuff, and some positrons. And so the fuels, you start with hydrogen, and hydrogen's actually pretty cheap and extremely abundant. We can get it from seawater, so that's nice if we wanted to make a fission power plant. It produces very little radioactive waste. Big problem with the fusion reactions, the uranium plants, is they generate a whole lot of waste, and if something goes wrong because the chain reaction starts going on, and bad things will happen because it's self-sustaining. If something goes wrong with a fusion reaction, you shut it down and it instantly shuts down. You take away the heat and it's gone. Since if you find a way that you can't get an explosion, you shut it off and it's shut off because it needs that energy. It cannot make its own energy. It needs that initial energy. So there's no danger of a meltdown. So that's nice. So the problem, however, is we have no way of doing this. Anytime we can make enough heat to start this process, it blows up. We just can't control it, because if we control it, if we added a little less heat, well, then it's not going to work. Oh, what if we spread everything out so it's not enough to have an explosion? Well, then it's not going to work. We do not have a way of making a fission power plant, and that's a problem. If we did find a way, a lot of good things would happen. Price of energy goes down. All sorts of nice things will happen if we had fission for energy. Pollution, our main pollution, is in making power. Lots of garbage. We got to do something about our garbage. But also, a lot of pollution of the atmosphere is due to burning fossil fuels, cars burning those fuels, and things like that. So, coming up with fission that can reliably be used to power us is just going to be great for the world. But we can't do that yet. The only way we can get fission to happen is in a bomb. So yeah, they said, okay, the problem with hydrogen, we can't actually start with hydrogen because it's a gas. Deuterium is just hydrogen gas, also with heavier. So we start with LID, lithium deuteride, lithium with deuterium on it. Now that's a solid. And so we take this core of lithium deuteride here, and then we just wrap it essentially in a bomb, in a uranium or plutonium atomic bomb. Turns out we found it's tough to get. Uranium bombs are tough to make, but plutonium bombs are easier. So we just make an atomic bomb and wrap that atomic bomb around this core of lithium deuteride, and now you have a thermonuclear weapon because you set off the atomic bomb. Once you set off the atomic bomb, the fission reaction, it generates enough heat to set off the fusion reaction, the thermonuclear reaction. And because of this, now we've bumped up bombs to megatons of TNT, huge explosions. And yes, that's what I would call evil. All right, so let's not end on evil in this chapter, but we shall end this video on evil. How sad.